I'd like you to consider two displacements that I would like to apply to a particle. The first one will be represented by vector F1. So F1 is the vector that represents the first displacement, and the second displacement I would like to represent that by another vector which I will call F2. And if you'd like to replace F1 and F2, all you have to do is draw a vector from the tip of the first vector to the tail of the second vector and call that your resultant. Well, I always like to remind you that it does not make any difference whether you apply F1 first and then F2, or vice versa, F2 first and then F1. Notice that this vector is equivalent to F1 because it has the same magnitude and the same sense of direction, and that this vector is equivalent to F2 for the exact same reasons. F1 and F2 are what we call components, and of course R is what we call resultant. Well, I would like to apply to the same particle a different set of displacements. So let's try this one more time. Displacement 1 will be represented by vector F1, and it is straight down. The second displacement will be represented by a different vector, which I will call F2. And if I'd like to replace F1 and F2 with an equivalent vector, all I have to do is draw a vector from the tip of F1 to the tail of F2 and call that my resultant. I'd like you to always notice that it does not make any difference whether you apply F1 first and then F2, or vice versa, F2 first and then F1. Notice that this vector is equivalent to F1 because it has the same magnitude and the same sense of direction, and that this vector is equivalent to F2 for the exact same reasons. You again just created yourself a parallelogram. Well, what's the difference between the first parallelogram and the second? It's pretty obvious that the angle between the two components in the second parallelogram is equal to 90 degrees, as opposed to the angle between the two components in the first parallelogram is not equal to 90 degrees. That is why this is called orthogonal components. Orthogonal means perpendicular. It means 90 degrees. Well, I'd like to take this a step further and define an angle which I will call alpha. That means this is also alpha. They're equal to each other because they are alternate interior angles. If you look at the second parallelogram, by definition, sine alpha is equal to F1 over R, opposite over hypotenuse. If I were to rearrange that equation, I could write F1 is equal to R times sine alpha. And again, by definition, cosine alpha is equal to F2 over R, adjacent over hypotenuse. And if I were to rearrange this, I could write F2 is equal to R times cosine of alpha. Well, you might think just because F1 is the component that is in the vertical direction, F1 is the component that is in the vertical direction, that is why I will always associate that with sine. And just because F2 is the component that is in the horizontal direction, F2, the component in the horizontal direction, that I will always associate that with cosine of alpha. Well, that's not correct. That is absolutely not correct. It has nothing to do with that. In fact, it has everything to do with the definition of sine and cosine. By definition, in orthogonal components, where the components are 90 degrees to each other, by definition, sine is always opposite over hypotenuse. If you look at F1, F1 is the component that is opposite of alpha. That is why I associated F1 with sine of alpha, because by definition, sine is always opposite over hypotenuse. That is why I'm always associating the opposite component with sine of the angle, as opposed to F2 is adjacent to the angle. Well, let's look at the definition of cosine. Cosine in orthogonal components is always adjacent over hypotenuse. And if you look at F2, F2 is the component that is adjacent to the angle. That is why I'm associating it with cosine alpha, because by definition, cosine is always equal to adjacent over hypotenuse. That is why when I am looking at the component that is adjacent to the angle, I will always associate that with cosine of the angle. I'd like you to always remember that when you are trying to find the component that is opposite of the angle, you always want to think of sine of the angle. And when you are trying to find the component that is adjacent to the angle, you always want to associate this with cosine of the angle. Well, let's try this. I have 3 exercises. Let's try the first one. I have a vector, and it is called vector A, and it is 70 degrees with respect to the positive y-axis. I am interested in finding the x component, so all I have to do is project it onto the x-axis, and I will call that A subscript x because that is the component along x. And if I'm interested in the component along y, all I have to do is project it onto the y-axis, and I will call this AY because it's the component along y. Well, let's find out what these 2 terms are in terms of the angle 70 degrees. AX is this component. Well, this component is equivalent to AX, and that component is opposite of 70. Opposite, I'm always going to think of sine when I look at the component that is opposite of the angle. So therefore this will be A times sine of 70. And because it is to the left, I'm going to put a negative sign in front of that term because positive x is to the right. AY, the component along the y direction, is equal to, well, that component with respect to 70 is adjacent to 70, so therefore this is A times cosine 70. Okay, well, let's try the second exercise. I have a vector that is 200 Newton. It makes an angle of 10 degrees with respect to the negative x-axis. I am interested in the x component. I'm projecting it onto the x-axis. I'm interested in the y component of 200 Newton, and I'm projecting it onto the y-axis. The x component that is adjacent to the 10-degree angle. Therefore, this will be 200 cosine 10. And because it is to the left, I must put a negative sign in front of that term. The component along y is equivalent to this component. That component is opposite of the angle 10 degrees. So therefore, this will be 200 times sine 10. And again, I must put a negative sign in front of that term because positive y is up. The third exercise, I have a vector which has a magnitude of 5 inches and it makes an angle of 35 degrees with respect to the positive x-axis. I'm interested in finding the x component projected onto the x-axis, and that would be equal to 5 cosine 35 because it is adjacent to the angle 35 degrees, and I'm projecting it onto the y-axis. That would be my component of the 5 inches along y, and that component is equivalent to this component, which is opposite of 35 degrees, so therefore this is 5 times sine 35.